This is the 10th lecture, and we are going to talk about small signal amplifiers, mid frequency analysis. Let us first explain the terms small signal and mid frequency. As you know, the DC operation of a transistor lies on the load line, on the DC load line, and DC load line starts at VCC and ends at VCC divided by R sub C. Alright, this is the DC load line, and the Q point is somewhere here, and through the Q point you can draw an AC load line. If the AC load is different from DC load, then you can draw an AC load line whose slope is minus 1 by RL prime, which is equal to parallel combination of RL and RC. Okay, this is known, and therefore the operation of the transistor, the AC operation of the transistor or the signal operation is on the AC load line, which virtually means, what is the AC load line? The AC load line is described by this: VCE is equal to minus RL prime I small I subscript small c, which means that when the incremental current is 0, the incremental voltage is also 0, or I could write this as VCE cap CE, yes, minus capital V CE, that is the DC part, alright, equals to minus RL prime I sub capital C total collector current minus the DC collector current. And since these are at the Q points, we say IC Q, and here also we add VCEQ. It is as if in the operation, in the AC operation, the axis of the current and voltage, they are shifted from this point to the Q point. Is that clear? You see, when VCE, total VCE is equal to VCEQ, the voltage, collector emitter voltage is 0. When the collector, total collector current is equal to the Q point, DC collector current, the current is 0. So it is as if this has been transferred to this point, and AC operation is now on this green line. Okay, AC operation, that is, if the incremental voltage, if the incremental incremental base current increases, if the base current increases, then you will go up on the green line. If the base current decreases, you will go down on the green line. But these variations are small compared to VCEQ or ICQ. They are small quantities. That is why it is called a small signal operation. Okay. You also know that the characteristics are like this. They are almost parallel lines, and if our operation is, let's say, limited between this point and this point, then the total excursion around the Q point is small enough to consider the device operation as perfectly linear. That is, for equal increments of IB, there will be equal increments of IC collector current, and there would be equal excursion of VCE, the collector emitter voltage. So it is not only small signal. If it is small signal, then it is guaranteed that the operation shall be linear operation. Okay.
Could you please repeat?
Yeah. So the point is, our AC operation, we are talking of AC operation. AC operation is confined on this AC load line, the green line, and since the excursion of of base current, which is the exciting signal, would be small, would be around this point, that is, it would either go up on the green line or go down on the green line. If the excursion is small, then equal increments of IB will cause equal increments of IC and equal swing of VCE, and therefore, and when the incremental base current is 0, the incremental collector current is also 0, and therefore it is a linear system. It can be treated as a linear system, although the transistor itself is a highly nonlinear device. But as far as AC operation around a well chosen Q point is concerned, well chosen, I have already told you how to choose it, then the operation can be thought of as linear, and the analysis becomes very simple. Very simple.
And why is it called small signal?
We are considering only small signal. Now, who prevents you from applying a large signal in a transistor? If a large signal operation is required, then we shall have to go into nonlinearities. There is no way out. What we are considering now is either a voltage amplifier or a current amplifier, where the excursions on the Q point will be small. If the excursions are large, for example in an audio power amplifier, then we shall have to go into nonlinearities, and we shall have to go into the actual characteristics to be able to analyze and synthesize such a power amplifier. Okay, that we shall come later on. But currently we confine to small signal, and small signal implies that the operation is linear. These two are almost synonymous, small signal operation and linear operation. Because of small signal, it is linear operation. The other term that we are using is the mid frequency. Mid frequency is the frequency at which the coupling capacitors C1, C2 and the bypass capacitors can be considered as infinitely large. That is their reactances approximately are 0. X1, X2, Xe tend to 0. 1 by omega c tend to 0. The frequency and the values of capacitors are such that they tend to 0. In other words, the coupling capacitors act as perfect couplers, and the bypass capacitor acts as a perfect short circuit. This is what we assume. Okay, mid frequency. We also assume that the transistor internal capacitances, well, there are capacitances because you have a reversed biased PN junction in the collector region, and you have a forward biased junction in the emitter base. Both of them have capacitances. In addition, the base to collector may have a capacitance. All these capacitances, which we shall see C pi, we shall call them later C pi, C mu, and there is also a capacitance C0 across the output. There are basically 3 capacitances that you have to take care. We assume that at mid frequencies they tend to 0. In other words, their reactances X pi, X mu, X0 tend to infinity, so they can be ignored. Okay, the 2 sets of capacitances are ignored due to 2 different reasons. One is these are very small and therefore their reactances can be neglected, they are open. These are very large, therefore their reactances can be considered as short. Okay, if that is so, then at mid frequency we can only work with resistive equivalent circuit. Okay, nothing else. We have already seen a very simple equivalent circuit of a transistor. That is, we have said that if this is the base and this is the emitter, a common emitter, and this is the collector, this is the emitter. If the emitter is common, then we have already come across at various points of time. I have kept on mentioning that there is an internal base B prime, and that there is a resistance Rx, which is the base spreading resistance of the order of 100 ohm or so, and between B prime and E there is this diode resistance R pi. R pi is KT by QIB, the DC IB. Okay, all right. And between the collector and the emitter there is a resistance which is the early resistance R0, which is equal to VA divided by I sub C. You see, IC and IB, they are related to each other. One is beta times approximately. and therefore I could express this also in terms of IC if I so desire, all right. And then you have, if this current is I sub B, then you have a current source which is beta times I sub B, okay. And we also said that this current source could alternatively be replaced by a voltage controlled current source. Here it is current controlled, beta IB is controlled by another current I sub B. If I take the voltage across this as V pi plus minus, then I could write this as GM times V pi, and obviously the relationship between R pi, GM and beta is that the product is equal to beta. This is one of the circuits that we have mentioned again and again during our analysis of DC biasing and device operation. The only other thing that is needed for an exact equivalent circuit, the only other thing that is needed is to add between the base, internal base and the collector. Let me do this with a different color. The only other thing that is needed is to add a resistance, and this resistance is called R mu between the collector and the base. If we add this resistance, then this becomes the so called hybrid pi equivalent circuit. Why it is a hybrid pi? Well, that it resembles a pi is doesn't have to be explained. It's like a pi, okay. There is a connection from here to here, there are connections in this direction, okay. This and this makes it a pi. Why it is hybrid should be clear after a few minutes when I discuss what is a hybrid equivalent circuit. So this is the circuit that we shall mostly be using. Let me recall the values. Rx is of the order of 100 ohms, R pi of the order of a K, R mu is of the order of megs, tens of megs. Typical value is 13 meg, and that is why we have not mentioned it so far. We didn't want to complicate life. We have to complicate life if we have a capacitor across it whose reactance is comparable to R mu or other resistances in this circuit. We shall see that later, but mostly we shall be fortunate to be able to ignore R mu. If R mu is included, life becomes miserable, analysis becomes miserable, so is design, okay. Then beta is of the order of 100, all right. Beta is of the order of 100, and R0 is also of the order of a meg. R0 appears due to early effect. What is early effect? That the collector characteristics are not perfectly parallel to the current axis, not current axis, to voltage axis, okay. It's slightly inclined, and this inclination is taken care of by R0. You also notice that GM is equal to beta divided by R pi, okay. GM is beta divided by R pi, which I can write as beta divided by what is R pi, KT by Q I sub B. Now beta times I sub B, beta times I sub B is approximately I sub C, so it is I sub C divided by 26 milliampere at the room temperature, millivolt, okay, wonderful. If I sub C is expressed in milliamperes, if this is expressed in milliamperes, then these two cancel, and I have simply 0.04 approximately times I sub C, where I sub C is in milliamps, okay. So if I know the collector current, then I know GM, and if I know GM, beta is given, then I can calculate R pi, or if I sub C and R pi are given, then I can calculate beta. The three parameters are related, and this is the circuit that we shall be using mostly. But why is it called a hybrid pi? Because this is a modification of the so called hybrid two-port equivalent circuit. Now the hybrid pi equivalent circuit took care of the physical phenomenon that is occurring in the transistor, that there is an internal base, that between the internal base and the emitter there is a junction, okay, that is how you calculated R pi and so on. The hybrid two port equivalent circuit does not take care of any of this. It simply says blindly treats the transistor as a three terminal device, base, emitter, base, collector, collector and emitter. And it says that if you consider AC equivalent circuit, the voltage here is VBE between base and emitter, the current here is I sub B, the current here is I sub C, and the voltage here is VCE. Try to learn distinguishing between capital C and small c. Okay, capital C I shall write like this, small c I will write like this. Okay. So the hybrid two port equivalent circuit treats the transistor as a black box. Okay. If you want the color black, well, I can. It's a black box. Okay. I don't know what happens inside. What I can do is to have the terminal voltages and currents. Okay. I can apply two sources. I can measure two responses. I could apply two voltage sources and measure two responses. Then I get the so-called Y parameters. Have you done the circuit theory two port parameters? Not yet. Okay. Right. So I will not go into that. What I will say is that one of the ways of describing such a black box is to take the input voltage VBE and the output current I sub C. Okay. These are the responses due to two sources. One is the base current I sub B and the other is the collector emitter voltage VCE. And since it is a linear operation, in small signal operation it is a linear operation, VBE and I sub C, these two responses, you know what are the sources now? Signal sources are a current source at the input IB and a voltage source at the output VCE. Alright, I can apply only two sources, measure two responses. I cannot apply a current source and a voltage source both here, can I? I cannot, okay, because that will be a degenerate condition. Now due to these two sources I measure the responses VBE and IC, and since it is linear, you know in a linear system superposition holds, therefore the response must be superposition of these two with appropriate constants, alright, and this constant is written as HIE, okay, these are constants, plus HRE, this constant is written as HRE. Similarly the collector current is written as HFEIB plus HOE VCE. Okay, this is the genesis of the H parameter equivalent circuit or the hybrid. H stands for hybrid, and why it is hybrid is because the dimensions of the constants are not uniform. You will see later in circuit theory course that the dimensions are either all impedances or all admittances. Okay, this is a mixture. You see, what is the dimension of HIE? This is an impedance. HRE is a dimensionless constant, HFE is a dimensionless constant, and HOE admittance. So you have impedance, admittance and dimensionless constants. HRE, as you can see, is a voltage transfer function. HRE is the ratio of VBE to VCE with IB equal to 0. Similarly, HFE is a current transfer function. HFE is IC divided by IB with VCE equal to 0. So you have all kinds of things. You have ratios of currents, ratios of voltages, ratios of voltage to current and ratio of current to voltage, and therefore this is a mixed set of parameter and it is called a hybrid set or H parameter description. H parameter. description. Now I must explain the symbols, the subscripts. Let me write it again. VBE is equal to HIE I sub B plus HRE VCE, and I sub C is equal to HFE I sub B plus HOE VCE. The second subscript here, E, stands for common emitter, CE, common emitter. If it is a common base, then we shall replace them by small b. If it is a common collector, then we shall replace the second subscript by small c. Is the point clear? We shall mostly consider the common emitter parameters, okay, because the common emitter is the easiest to measure and to handle in design and analysis, okay. So this second E stands for common emitter. The first I, this I stands for input. As you can see, HIE is equal to VBE divided by IB under the condition VCE equal to 0. Naturally, VBE and IB are at one single port, at the base emitter port. VBE is the voltage and IB is the current that it drives. So this is the input, this is the quantity measured at the input terminals, and that is why this subscript, first subscript I, is there. In a similar manner, if you look at HOE, this is an output parameter, because HOE is I sub C divided by V sub CE under the condition IB equal to 0. So this stands for output. On the other hand, the other two parameters, if you look at HRE, it is equal to VBE divided by VCE under the condition IB equal to 0, which means that if you apply voltage across the collector emitter terminals and measure the voltage across the base emitter by making IB equal to 0, that is by making base open circuited, no current enters into the base, then this is the ratio HRE, and you see the transistor normally operates from base to collector. Base is the signal input and collector is the signal output. Now here you are working in the reverse direction, that is, apply a signal at the collector emitter and take the signal out at the base emitter. So this R stands for reverse voltage ratio, reverse. The R stands for reverse. And if you look at the other constant HFE, HFE, as you can see, is the ratio of I sub C divided by I sub B with VCE equals to 0. Now this is the ratio of two currents. What are the currents? The input is the base current and the output is the collector current, under the condition that the collector emitter port is short circuited as far as AC signals are concerned, and therefore this is a forward current transfer ratio, forward from left to right, and this F therefore stands for forward. Okay. So let me put down the other two also. HIE is VBE divided by IB with VCE equal to 0. No, let me write them clearly. HIE is VBE divided by I sub B VCE equal to 0, and HFE is equal to I sub C by I sub B VCE equal to 0, and HRE is equal to VBE divided by VCE with IB equal to 0, and what is remaining? OE is equal to I sub C divided by VCE with IB equal to 0. Okay. These are the definitions of the four parameters, H parameters. Why are you interested in H parameters? If hybrid pi is good enough, why are you interested in H parameters? That is because H parameters are the easiest to measure experimentally. they are easy to measure. And why is it easy to measure? Easy to measure because VCE equal to 0, that is the collector emitter junction short circuited, means that you have to include a resistance from collector to emitter which is much less compared to what resistance it sees. From the collector to emitter, what is the resistance seen by an outside source? It is R0, the early resistance, which is very, very large. And therefore, between collector and emitter, even if you introduce a 1K resistance, it acts as a short circuit. Isn't that right? It is very easy to short circuit the collector emitter junction, collector emitter terminal, because the impedance faced by an external source at the collector emitter terminal is very large. If you have a very large impedance source, it is very easy to short circuit this. Alright. On the other hand, IB equal to 0, IB equal to 0 means open circuit. Alright, open circuit the base. Now you know that if you connect an external source between the base and emitter, what resistance does it face? It faces Rx plus R pi of the order of a K. And therefore, if you have a source, of let us say internal resistance 100K, then virtually this is open circuit. Agreed? So it is very easy to open circuit a low impedance device, and it is very easy to short circuit a high impedance device. So experimental measurement of the H parameters, they are very easy, and mostly the manufacturers specify small h parameters rather than the hybrid pi parameters, and the hybrid pi parameters usually are to be obtained from the h parameters, and the relationship is very easy to derive. What you do is, first you write this relationship, that is VBE is equal to HIE I sub B plus HRE VCE, and I sub C, I beg your pardon, I sub C is HFE IB plus HOE VCE. If you look at these relationships, one thing is obvious, that we can draw an equivalent circuit like this. An equivalent circuit like this. Between VBE and IB, the relationship is there is an HIE, this current is IB, and then there is a voltage controlled voltage source. So I draw a voltage source which is HRE VCE. Alright. The other one is the second relationship, I sub C, this is the collector current, this is I sub C. I sub C is the sum of two terms. One is HOE VCE, and HOE is an admittance. So if I want to write in terms of resistances only, I should write 1 by HOE, and then a current controlled current source. So I have HFE IB. And if you look at this equivalent circuit, this is an equivalent circuit that we have artificially constructed, alright, from these relationships by using two controlled sources. One is a voltage controlled voltage source, takes care of reverse transmission, that is from the output to the input, and a forward transmission current controlled current source HFE I sub B. Alright. By utilizing these two sources, which incidentally shows that the device is an active device. If these two are not there, there is nothing, no activity in the device. The presence of a current controlled current source and a voltage controlled voltage source shows that the device is active. Now how does it differ from the hybrid pi? All that it differs is that if this is absent, if this source is absent, then you see it is exactly the hybrid pi, except for the connection between base and collector. So the hybrid pi circuit has a similarity to the hybrid parameter equivalent circuit, and that is why the name hybrid pi. Is the point clear? These are the H parameter. This is the H parameter model. Slight modification of this leads to the model that we are interested in, which is derived from physical considerations, and that's why that is called a hybrid pi model. Let me draw the hybrid pi model side by side. What we have is between base and emitter we have Rx, R pi, then we have an R mu, then we have, if I call this a V pi, then this is Gm V pi, and then we have R0. Mind you, we are considering only mid frequencies. That's why no capacitor here. Otherwise, we shall have to complicate things by including a capacitor here between the terminals of R pi, which you shall call C pi, a capacitor here between the terminals emitter base prime B prime and C, which you shall call C mu, and a capacitor here which you shall call C0. Okay. This will make the circuit, the hybrid pi parameter equivalent circuit, complete. But since we are considering mid frequencies, this is enough. This suffices. And the relationship between the H parameters and the hybrid pi parameters can now be very easily constructed. Okay. That is, you calculate, for example, okay, let's see. You calculate HIE from the hybrid pi equivalent circuit, Rx, R pi, R mu, Gm V pi, R0. Okay. How do I calculate the HIE? HIE is the input impedance with the output. Yes, what do I do to the output? Short circuited. So I make it short circuited. If it is short circuited, you see R0 goes off. The current Gm V pi, well, it shall be there. It shall be there. It goes like this. And the current here, suppose R mu was not there. Suppose R mu was infinity. Then HIE would have been simply equal to Rx plus R pi. On the other hand, if R mu is not equal to infinity, one can easily calculate by circuit analysis that HIE, I have the relationship, is equal to Rx plus R pi divided by G mu R pi plus 1. This is the correct relationship. Okay. If R mu is not infinity, and I shall leave this as an exercise to you to find out that this is correct. G mu, all small g's are equal to 1 by R. So G mu is equal to 1 by R mu. Now usually as you see, G mu R pi is R pi divided by R mu, and R pi is of the order of a k. R pi is of the order of a k, and R mu is of the order of 10 meg, and therefore this quantity G mu R pi is very small compared to unity, and therefore this does approximately become equal to Rx plus R pi. Even if G mu is not 0, that is, even if R mu is not infinity, this is approximately correct. HIE is Rx plus R pi. So if you are given, now the question comes, if you are given HIE, a measured quantity, alright, then how do you calculate Rx and R pi? Obviously R pi has to be calculated from the collector current, and then you can calculate Rx. Is that correct? Alright. Next, you can also show that HFE from this equivalent circuit by applying the definition, that is I sub C divided by I sub B. These are all incremental quantities under the condition VCE equal to 0. You can show that this is equal to R pi Gm minus G mu. Again, G mu is 1 by R mu. I leave this to you to show divided by 1 plus r pi g mu. And once again you see that g mu would be very small compared to gm. Gm is of the order of 0.04 I sub c in milliamperes, okay, and g mu is a very small 1 by 13 meg, and therefore this is approximately, you can ignore this and you can ignore this, already we have shown that. Therefore HFE is approximately equal to r pi gm, that is equal to the glorious quantity beta, okay, r pi gm. So HFE, it is, if it is given, you can directly equate it to beta, no problem. And since you know gm, you can calculate r pi. If HFE is given, you can calculate gm as 40 times I sub c, okay, 40 times, or 0.04 IC if IC is a milliampere. Therefore you can calculate the third quantity. These three are intimately related. In a similar manner you can show that HRE, the reverse voltage transfer coefficient, is given by r pi g mu divided by r pi g mu plus 1. This can be measured, and since r pi g mu is much less than unity, this is approximately equal to r pi g mu, and if this is much less than unity, this can be approximated to 0. Typical value of HRE, HRE, what is the dimension? It is dimensionless. It's a product of conductance and resistance. It's dimensionless, and the typical value is 10 to the minus 3 and is almost safely neglected by all electrical engineers except those who are very fussy. HOE, you can show, this is not a very simple exercise. For HOE you have to connect a voltage source at the output and find out the current by open circuiting the input, okay, and this comes out as G0 plus G mu plus r pi G mu. It's a fairly elaborate expression. As I said, I shall check whether you have done this yourself or not. I leave this to you as an exercise, and I have my own ways of checking. You see that this quantity is approximately 0, okay. What is approximately 0? No, this is not approximately 0. It is approximately r pi g mu gm, and this is equal to G0 plus G mu 1 plus beta. This 1 can be ignored, and G mu beta, G mu being a very small quantity, can also be ignored. Therefore ultimately it is approximately G0, which is the inverse of the early resistance, okay. So if the H parameters are given, one can calculate the hybrid pi parameters, and this mostly you shall have to do. Because of historical reasons, the manufacturers have still not educated themselves. They usually give the H parameters rather than the hybrid pi parameters, and as a circuit engineer you shall have to calculate these parameters from what is given. Let us take a typical example. 2N222A transistor at 25 degrees C has the following operating point. I sub C is 1 milliampere and VCE is 10 volt. At this Q point, the parameters measured or given by the given by the manufacturers are HFE is 100, HIE is 2700 ohms obviously, HRE is 0.0002, 2 times 10 to the minus 4, indeed a small quantity, and HOE is 15 micromole. The question is to find the hybrid pi parameters, okay. Find the hybrid pi parameters. The first thing that we do is find out GM. GM is I sub C 1 milliampere divided by 26 millivolt. So this is not exactly 40 but 39 millimoles. Okay, so you know GM, and HFE has been given, and therefore HFE is beta, therefore beta is 100, which means that you can find out R pi. R pi is equal to 100 divided by 39 millimole. Please take care of the dimensions, don't make a mistake, and this comes out as 2600 ohms. HIE has been given as 2700 ohms, therefore Rx is equal to simply 100 ohms. If in your calculation R pi comes out as greater than HIE, then there is something wrong. You must go back and check your calculation first, then check manufacturer's specification. Then if your calculation is right, manufacturers must have made a mistake, and often such mistakes occur. That's why I am warning you. R mu is equal to, you can show that it is R pi divided by HRE, okay, from those relationships, and you can show that this is equal to 2600 divided by HRE is 0.0002, and this comes out as 13 meg, can be safely ignored in circuit calculation. G0 is HOE minus GM HRE. This also you can show from the previous relations that we had established. I am not deriving this, and this comes out as 139 K. No, this is 1 by 139 K. Alright, so R0 is 139 K. This is a good point to stop.